Hello everyone, welcome to this video. In this video, we are going to learn about Sparse Variational Gaussian Process using OpenMathAI. So, let's get started. What is a Sparse Variational Gaussian Process? A Sparse Variational Gaussian Process is a probabilistic machine learning model used for nonlinear regression and uncertainty estimation. Unlike traditional regression models, which provide only a single predicted value, an SVGP predicts both the output and the confidence associated with each prediction. An SVGP works by learning a smooth nonlinear function from the training data using a small set of representative inducing points. Instead of using every training sample during prediction, it uses these inducing points to approximate the full Gaussian process, making the model much faster and more scalable for large datasets. During prediction, the model receives new input values and compares them with the learned inducing points. It then estimates the underlying function and produces both the predicted output and its associated uncertainty. We will use a sensor calibration dataset for the SVGP model. This dataset contains 2,000 data samples. The input features are POSX and POSY, and the target output is sensor error. The sensor error depends on the nonlinear relationship between the sensor position coordinates. During training, the SVGP learns these nonlinear spatial patterns while optimizing the inducing points and variational parameters. Once the model is trained, OpenMathAI uses a learned Gaussian process, an inducing point, to predict the sensor error for new sensor positions without retraining the model. So, let's get started. Open OpenMathAI. In this demonstration, we use sensor_calibration by using SVGP model. Click Create New Project. Enter the project name as SVGP. Choose a folder location to save the project, then click Save. To import your dataset, either click Load Example Dataset or browse for Dataset to import your own CSV file. Once the dataset is loaded, verify that it contains all columns before proceeding to model training. Scroll down to view the first 10 rows of sample data. Click Continue to Configuration to proceed. Configure the dataset by specifying the input features and output target. There is also a feature called Ignore, which can be used for columns that should not participate in model training. Select the input and output columns manually or use Smart Suggest for automatic recommendations. There is one more feature, Signal Diagnostics. There is a free columns. First one is column its tell which features on the dataset like inputs and outputs name. Second one is VIF if it tells how much correlation of the features. Third column is status if it's OK, moderate, high, redundant, and constant. Review the selected configuration. Click Proceed to Model Design. Choose a model from the available machine learning models. OpenMathAI recommends suitable models and features based on the dataset. For this demonstration, select the SVGP model. View the model overview, pros, cons, and real-world applications. Click Proceed to Training. You will see the selected model. Click Train Models. Review the training configuration, test data split, which determines a percentage of data reserved for testing and validation. Review the model parameters and pre-processing settings. And also the another feature is added that is trained from scratch or continue from use model. If you train this model before you use that option, modify the configuration if required. Click Start Training to begin the training process. After training is complete, review the following performance metrics. R² measures how well the model explains a variation in the output data. Range 0 to 1. MSE, mean squared error, measures the average squared difference between actual and predicted values. RMSE, root mean squared error, the square root of MSE. RMSE is expressed in the same units as the output variable, making it easier to interpret. Engine time, the time required for the generated model engine to execute and produce predictions. Lower engine time indicates faster model execution, which is important for embedded systems and real-time applications. Fit quality, an overall assessment of how well the model fits the dataset. It is generally derived from tricks such as R², RMSE, and residual errors. Model accuracy is commonly estimated using the R² value. Example, R² equals 0.95 accuracy, almost equal to 95%. Click Fit to Window. You will see 3 types. Fit to Window, Comfortable, Compact. Then the Clear History. If you click that, it will clear the history before its trained model. Another is Deselect and select all trained model for export. Click View Curves. You will see the diagram of R-squared residuals and residuals diagram. Click Math and Code Preview. View the generated mathematical equation and source code. OpenMathAI provides expression of the data, detailed explanation of the expression, and an implementation code. Return to the result page and click Deploy Status. Click Export Model. Choose the required export format: ANSI MCU Fixed Point C, FMU 2.0, FMU 3.0, Verilog RTL, VHDL RTL, Python Bundle, ONNX Hub. You can choose any of these formats and export. You can also download the free trial versions of OpenMathAI and Twin Simulate. Thank you. Stay tuned for more OpenMathAI demonstration.